Okay, so quiz is going to be on Wednesday, and it's going to cover, I think, all of Chapter 5. Let's go ahead and plan it now. I'm pretty sure that it will. We'll probably finish Chapter 5 on Friday, and there are really only several big topics. Work, we've already seen that. I remember work is equal to FD cosine theta. We'll work some problems like that. And then also energy. And we'll see two different types of energy. We haven't seen this in class just yet, but we'll see two types. That's potential energy and kinetic energy. We've seen those in Word. I think we did. Potential energy is the energy of a position, that if I have an object and it has the potential for motion, then we say that it has potential energy. And that's equal to m times g, which is the force due to weight, times the distance that you move it, which is h. So see, as I take this object and I apply a force weight to it, moving it up, I've done work on that object. Work is force times displacement. And so my potential energy then is that force times the height, h. By the way, will have these equations for the quiz, and moving forward, you'll have an equation sheet. That equation sheet is on the website. It's right here, and you'll have this on all future quizzes and exams going forward, okay? Because we're just going to have more equations building up in some of these chapters. By the way, the next exam will probably be chapters 5 and 6. It might have a little bit of chapter 7 in it. Kinetic energy, which is the energy of motion, is 1/2 times the mass times the speed squared. And then finally, the other idea is the conservation of energy. And the conservation of energy just says that in a system where energy is conserved, that is a system where conservative forces are acting. Conservative forces are simply forces where energy is conserved. That in a system where you have these forces acting, the initial energy, that's EI, is equal to the final energy. Now we'll look at some problems like this. Since we're just dealing with mechanical energy, which we talked about last time, that would be to say that the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. Three big ideas. We've already covered a couple of those, and you'll probably have 3 to 4 questions from each topic here for the quiz coming up. And that'll be about roughly half your exam. Let's look at some work problems first, and then we will do...
Just a quick one. Conservation of energy, you said that's for the system, right?
Yeah, for the system. So you'll have an object that's... we will only deal with one object within that system. I'll show you what I mean. It'll become clear when we do it. There was one other thing, a fourth topic, and that was the work energy theorem. When I do work on an object, I cause it to change its energy. It either gains or loses potential or kinetic energy. Okay? Okay, so like for example, here's number 12. This is a problem where you have to determine the amount of work that's being done by a force. This is how we define and how we determine what is how we determine the amount of potential energy an object has. I have an object that has a weight of 200 newtons. I know that because it's 20 kilograms. M times G, that's the weight. It has a 200 newton. And it requires then 200 newtons to lift it through a certain distance. So that is the force that I have to apply. And then it's exerted over a distance of 2 meters. That's what this 2 meters is right here. So the work that I do on this object is equal to FD cosine theta. Now in this case, the angle theta is the angle between the force and the displacement, and so that's equal to 0 degrees. You will see problems where theta is just not mentioned. Almost always, that angle theta is going to be equal to 0 degrees. I'll show you one where that's not the case. But in this case, the angle theta is 0 degrees, and so cosine of 0 is equal to 1. Elena?
That's what I'm trying to look at. Is by
Okay. Okay, because we know that our force that we're exerting, right? You lift this object, so you have to exert an upward force, is upward. F is up, and then the displacement is also in the upward direction. Oh, because you're lifting this object. If I lift this object going up, then its displacement is in the upward direction. Is that, you understand what I'm saying? Yeah. Yeah, that's right. So when you know what the distance is, or the displacement and the force, if they're in the same direction, that angle theta is equal to 0 degrees. If they're perpendicular to one another, that angle theta is 90 degrees. And then the other one that you're most likely to see is where the the force and the displacement are opposite one another. And in that case, that angle theta is 180 degrees. Cosine of 0 is 1. Cosine of 90 is 0. And the cosine of 180 is negative 1. This almost always comes up when we're dealing with friction. Okay? No, you don't need to memorize that. I mean, if you forget, you can just put it in your calculator. But it is an important idea that if I have a force and a displacement that are perpendicular to one another, then that work is equal to 0. Now, if you know this angle is 90 degrees, then you could always say, well, I know that work is equal to FD cosine theta. And you could just say, well, what is the cosine of 90? And you would find that the cosine of 90 is equal to 0. Okay? So anyway, on this one, if I'm finding the work, returning back up here, work is equal to FD cosine theta. I determine that this cosine theta is equal to 1. So that's going to be my force, which is 200 newtons, times my distance, which is 2 meters. So the answer is 400 joules. That means that I've done 400 joules of work on this object. Let's find another one that's something similar. I don't know that there's one on this exam, but let's go to another one. No, I don't see one. Let's go back and do conservation of energy. Okay? We'll do some more of these work problems tomorrow. But those are mostly just putting in the force, putting in the displacement, and taking the product of those two. Let's look at conservation of energy. So that is this category of problems. And in the conservation of energy problems, you look at a system. Like, let's consider this one, number 1. I have this bead that begins at a certain height, and it moves through changing its height. Kind of like a roller coaster. You ever been on a roller coaster? Yeah? So it's kind of like that. I have an object that starts at a certain height and then moves down and comes back up again. Now, as it moves through, the energy is always conserved. The total amount of energy that the object has is always the same. So the potential energy plus the kinetic energy will always be constant. Then in some places, though, it's going to have 0 potential energy, but a maximum amount of kinetic energy. And in other places, it might have 0 kinetic energy, but a maximum amount of potential energy. So if you imagine this is the kinetic and potential, sometimes one will go up and the other will go down. The opposite will happen, but the sum of those two will always remain the same. That's the idea behind the conservation of energy, that I always conserve energy. I never lose any energy in these systems. So when you look at a problem like this, I have 3 positions, A, B, and C, and I want to determine what type of energy does it have in each position. So first of all, at point A, I recognize that it has a certain speed. That means that at point A, the object has kinetic energy, but I also see at point A that it has a certain height. Now remember, potential energy is equal to mgh, and kinetic energy is equal to 1/2 mv squared. So the potential energy is 0 when what is true? When is the potential energy of an object equal to 0? I understand where you're coming from, but no, that's not the answer. It's not completely wrong, but it's not exactly right either. Okay, that's true. Yeah, but I'm looking for something simpler than that. Just look at the equation for potential energy. When is the potential energy equal to 0? When which of these variables is equal to 0? M, G, or H? H, right. So M is just the mass. If you have an object, you have a mass. G is always the same. So if H is equal to 0, then I know I have no potential energy. What about kinetic energy? When is it equal to 0? Right, when it's stationary. So for example, you have no kinetic energy right now because you're not moving. So at this point, I have kinetic energy and I have potential energy. At point B, what kind of energy do I have? Potential, kinetic, or both? I have only kinetic energy here because the potential energy is equal to 0. Potential energy is equal to 0 because the height is equal to 0. And what about at point C? What do I have? Potential, kinetic, or both? I have both. The reason I have both is that H is equal to 2, and then, you don't know this necessarily, but you probably do know it, that the velocity also there is non-zero. So it has kinetic and potential. So the answer for this is what type of energy does it have at point A? Is both potential and kinetic, because it has a height and it has a velocity or a speed. Now, for a calculation, this is the same scenario, and I want to know what is the speed of the object right here. Well, I know that at point A, it has both potential energy and kinetic energy. And at point B, it only has kinetic energy. And I know that the sum of those energies at point A have to equal the energy at point B, that the total amount of energy will always remain the same. So I'm going to have M times G times H. I'm going to go ahead and put in 5 meters right here. That's this 5 right here. Plus 1/2 M times 4 squared. That's this velocity right here, is equal to 1/2 mv squared. And v squared, or v is what I'm looking for. That is the speed of the object at position B. Now, I can get rid of my masses. They're all going to cancel out. I divide through every term by the mass m. So that's 50. 10 times 5 is 50. That's 8 equals 1/2 v squared. That's 58, or 58 divided by 1/2 equals v squared. So v is equal to the square root of 116, which is about 11, rounded up to 11. Okay, so that's a sort of a classic potential energy problem. And then notice too that there's a similar one right here where I'm asking what is the speed at point C. And you do a very similar thing where you say the potential energy at A plus the kinetic energy at A is equal to the potential energy at C plus the kinetic energy at C. Ian?
So you don't have to use B, like you only just need to use 2 blank.
That's right. Your energy remains the same throughout. So I could set the potential and kinetic energy here to here. Anywhere. I could say, this might be easier actually, since you now know the speed of the object at B, I could say instead that the kinetic energy at B is equal to the potential energy at C plus the kinetic energy at C. You see what I did there? Mel, you have a question? Or is it the same?
No, it was the same question.
Okay. All right. So that's the conservation of energy. And the problem that you have will be very similar to that. In fact, that's going to be your free response on the next exam. It's going to be a very similar question. If you look at all of the exams 3, you'll see that that's the first set of questions that you'll have. Something very similar to this. And that'll be on your quiz too. You probably have 2 questions, 3 questions like that. What was that? Oh, it's they're working on the ventilation. We have it's the building. This building is different from every other building on campus because all the air is fresh air. In every other building, they recirculate the air over and over again. But this building, all the air comes in through those big vents on the side in the courtyard over here. That air comes in, and then it goes out those big smokestacks up top because it's a lab building, and it helps to keep the fumes, out of the building. But it's difficult to maintain, so they have outside people come in to maintain it. Not even to maintain it. Like, there's no set thermostat where you just change the temperature. There's a computer program, and they have to get all the different rooms just right. It's difficult. Oh, I lost my projector? The projector went off? Okay, it's coming back on. I still have my computer up here. Go ahead.
So for the work problems, like the one that we did at first, is your angle always going to be 0, 90, or 180, or?
No. I'll show you one before we leave today, okay? Let's go ahead and look for one of those. I have to go back a few exams.
But it's still the same, like the same thing, you just add a different angle, right?
Yeah. Like, let's look at this one right here. Okay, so this one, number 12, right here, is asking, by the way, this is fall 18. Fall 18, number 12. This guy is pulling this block. And I want to know, what is the work done by the man on the block? So, I have this one force, 45 newtons, at an angle of 28 degrees. The quick answer is to say that the work done by the man on the block is FD cosine theta, where my force is 45 newtons. That's the work that's being exerted by the man, times my distance. He goes 5 meters across the floor, 5 meters, times the cosine of 28. And then whatever that answer is the answer to the question. Okay? Y'all know what it is? What is it?
It was 198.
Yeah, so the answer would be 200. Now this problem is actually a little more complicated. I mean, not this question, but there is another question that I could ask that I didn't ask. Let's look at that. What is the total work being done on the object? And that gets a bit more complicated. Let's take a look. I'm going to draw the free body diagram for this. Let me draw the forces first. This is my 45 Newton force. I have my weight, Fw, that's equal to 80 newtons, right? 8 times 10 is 80. I have my normal force, Fn, and then I also have a kinetic frictional force, Fk. Now, I can replace this force with two forces, which is going to be F cosine of 28 and F sine of 28. You'll see what I did there? I found the x and y components. Now, I want to know what is the total work that's being done on this object by the man and by the force. There are two forces that are in the same direction as the displacement, or in the same direction or anti-parallel, that is, in the opposite direction. They include this force right here, F cosine of 28, and Fk. Let's just say, for the sake of this problem, that Fk equals 2 newtons. Okay? It doesn't. It's more complicated because, as you know, you need to find Fn, and then you need to find the coefficient of kinetic friction, which is given, and then you need to calculate Fk. But that might come up on your exam. I don't expect it to come up on the quiz just now. Okay? Let's just say that the Fk is equal to 2 newtons. F cosine of 28 was what? 40 newtons. That's 45 cosine of 28. That's right now, isn't it? Can you do that? 45 cosine of 28?
Yeah, 39.7.
Okay, so F cosine of 28 is 40 newtons. So I imagine that I have this block with a 40 Newton force on this direction and a 2 Newton force in this direction. The work done by this force is 200 joules. The work done by this force is negative 10 joules. So remember, work equals FD cosine theta. I have a force of 2 newtons. I have a displacement of 5 meters. That's just told, I have that in a problem up here. And then I have my cosine of 180 degrees. So notice that my displacement is in this direction, but this force is in the opposite direction. So that's why I have 180 degrees. Anytime they're opposite directions, this is 180 degrees between those two vectors. That means that this is going to equal to negative 10 joules. So I have 200 joules here, negative 10 joules here. The net work, the total amount of work, is 200 minus 10, or 190 joules. Okay? Notice that in this problem, number 12 and 13, I didn't ask what is the kinetic frictional force. I probably wouldn't ask that on the exam. I'll give y'all a heads up if that's the case. That's drawing quite a bit back into chapter 4, but I might ask you that, but I will give you a warning if that's the case. Well, let's go ahead and assume it won't be on the quiz. It won't be on the quiz. Let's look at a similar problem that deals with this. This is in these categories of problems that we were looking at. This is this fourth category, the work energy problem. Yeah. It's about equal. Was that where you were hurt the worst in the last exam?
I actually did really good on the last one. But 99% of the time, yes.
Yeah, you're not alone. Most students, they do really well in the calculations, but then the concepts is really what trips them up. That's really the hard part. I think they think the math is the hard part, but that's not really true. It's not the math, it's the hard part. Yeah. You need to be careful about that, no?
I wasn't thinking straight.
Okay, let's look at this. This problem is asking, I have an inclined plane. Don't freak out. You're not going to have to rework the inclined plane because I actually give you the various forces that are at work. I have one force pulling up, and then I have another force that's pulling down. And I just want to know what is the total work done on the block. So this force does a work of 20 newtons times 2 meters. That's F times D. The displacement is up the inclined plane, right? Yeah, it's pulling it up the inclined plane. So that means that the angle is 0 degrees, and the cosine of 0 is, gosh, what's the cosine of 0? 1, right? When they're in the same direction, the cosine of that angle theta is equal to 1. So that's equal to 40 joules. On the other hand, this force, which is 5 newtons, does a work that's equal to 5 newtons times 2 meters. And so that's equal times the cosine of 180. Because notice this vector opposes the direction in which the block is going. Anytime the force is in the opposite direction, you're doing negative work. And I always think of like the frictional force. The frictional force always opposes the direction of motion. The frictional force always does negative work. That means that it's taking energy away from the object. So I have, this is equal to negative 10 joules, 40 joules, negative 10 joules, then the answer would be 30 joules. Well, they is me, and no, it's not to trick you. That's just the inclined plane. Well, you need practice, and you'll know that that's not really the angle. The angle that you're concerned with is the angle between the force and the displacement. That's always the angle that you're concerned with. You always want to ask yourself, what is the direction of that angle? Now, this problem is also work energy theorem. That's that work causes change in energy, that number 4 topic. And here I have the same situation, and I want to know what is the change in height for the object. Well, I already know the amount of work that I'm doing. I'm doing 30 joules of work. And so now I want to know what is the change in energy that brings about. Well, in this case, I'm changing the potential energy of the object. I'm putting this 30 joules of work into this object, and that's going to change its potential energy. That is 30 joules is equal to m times g times a change in the height. That's our equation for potential energy. So that's 30 is equal to the mass, which is 3 times 10 times delta H. So delta H is equal to 1 meter. This is just like the lab. You know, remember the lab with the inclined plane? This is exactly what we did in the lab. We had a force pulling it up, and we said, well, that has to equal to the weight of the cart times the change in height. Okay, so we've done work, we've done the work energy theorem, we've done the conservation of energy. So I think we've done them all. Let's just do some more. Ooh, number 4 is a good one. Let's think about this. I have a cardboard box. It has a speed as it slides across the floor. That speed is, we'll say it's to the right, and it's 2 meters per second. But there's a frictional force that is acting on this block, and it tells me that mu k for that frictional force is equal to 0.2. And I want to know how far does the box slide before it comes to rest. This object has some kinetic energy. That kinetic energy is equal to 1/2 mv squared. That's 1/2 times the mass, which is 3 kilograms, times its initial speed, which is 2 meters per second, squared. That's 6 joules. And half of 3 times 4, half of 12, that's 6 joules. That's how much energy it has right here. 6 joules of energy. But as it moves, watch this. As it moves, the frictional force takes away that energy. And what I want to know is how long, that is, what is the distance, d, over which that frictional force acts so that it takes away 6 joules of energy. I know that the work that it has to do is going to be negative 6 joules. It has to do negative 6 joules to take away all that 6 joules of energy. A frictional force, a dissipative force, takes energy away. That's why this negative, that's what the negative means, that it takes away energy. And that has to equal to F times D times the cosine of the angle theta between those two. Now the cosine of the angle theta is going to equal to what? Or what is the angle theta between F and D? F is right here. D is in this direction. What is the angle? 180. And we know the cosine of 180 is -1. So I get a -1 right here. So that takes care of that -1. I don't know what D is. I also don't know what Fk is. Now Fk, you're going to have to remember back to chapter 4. Remember that Fk is equal to mu k times the normal force. That's 0.2. That's given in the problem, right? The coefficient of kinetic friction is 0.2. Now what is the normal force for this object? Right. When you're on a horizontal surface, it's just equal to the weight, right? So the weight of this object, let's see, it has a mass of 3 kilograms, so the weight is 30 newtons. I just did m times g. And 0.2 times 30, that is 6 newtons. So I have a force of 6 newtons acting over a distance of, well, I don't know what. I can figure out the work done. So I have work is equal to minus 6 joules. That's equal to 6 newtons times a distance of, I don't know, times negative 1. So that means that my distance is 1 meter. Whew. That's kind of a difficult problem. But as far as calculations that you're doing, that's probably one of the more difficult. And it's not even really the math that's difficult. It's realizing that I have a certain amount of energy here, and that frictional force takes it away as it moves through this distance d. So that's kind of a combination of work and conservation of energy and the work-energy theorem all combined into one. Very good question. I haven't made out the quiz, but I was winking right there. Could y'all see me winking? Yeah, like it's a very good question, something that I would like to put on the quiz. I don't know if I will or not, but it's likely that you'll see something similar. Likely to see something similar to these conservation of energy problems. Like I said, they're on every exam, so you need to know those really well. And then likely to see something like number 4. Let's look at some conceptual, specific questions about this.
You don't have one force to look at all times. Like in this case, it's just friction force.
Not necessarily. I mean, the problem that we worked earlier, like this one right here, where we had to find the total amount of work that's being done, it didn't have one force, right? That I had to figure out the energy, or excuse me, the work done by both forces and then add them together. So no, you'll likely have a question where you have multiple forces, some of which are doing positive work, some of which are doing negative work. I probably won't require you to do all the vector addition like we did in chapter 4, like with the inclined plane. I would do something like this, where I go ahead and do that for you, and then I'm just testing, do you understand work and energy? You understand what I'm saying? Mm-hmm. Like, I'm not going to make you resolve the forces and add up all the forces, like the chapter 4 stuff that we did on the last exam. All right, we'll get the springs next week. I'm not going to do springs today. That's also possibly on the exam, on the quiz. I don't know. I'm going to tell you. So there are 2 other things that are really small things. One is power. Y'all are just getting a preview of the chapter to come. You know that, and that's good, right? Sort of see this before you see it in class. I think it's good. Power is just work over time, or energy over time. You might see one question like this on the quiz. It'll be mostly a straightforward question. So for example here, which expression represents power? A is energy, C is work, D is energy, so B is power. I'll write it out. Right, work over time, this is potential energy, this is work, this is kinetic energy. You'll have your equation sheet, so you'll see those things. Those things are all on the equation sheet. Let's skip up that one. Here's one of these where I'm asking for the basic SI unit for power. You'll likely see something like this on your exam, maybe on your quiz. Power is work over time. That's force times distance divided by time. That's more detailed, mass times acceleration times distance over time. So then that would be kilograms, meters per second squared, meters 1 over seconds. These are the basic SI units. That's kilograms meters squared per seconds cubed. You see how I did that? Whenever you get one of those units problem, just write down the formula. It'll be on your equation sheet. And then put in the basic SI units for each variable. So make sure you know what those basic SI units are, for example. And then also be aware that force is actually mass times acceleration. Okay, let's do a problem that was similar to one that we just did. Number 5 here. We've done this problem before. We did it in chapter 2, but there's a much simpler way to do it when you look at the conservation of energy. That's why I remember when I was a student, I learned this chapter, that it's like, gosh, that's a lot easier doing it that way than it was when we did kinematics. With kinematics, in this problem, we had to say, well, the velocity at the top is 0, find the time at the top, and then we can calculate the y position. But here, if I have an object that goes up, and I want to know to what height does it go, I just need to ask myself, what kind of energy does it have at each position? Well, down here, the potential energy is 0, because it's at a height of 0, and the kinetic energy is equal to its max, which is 1/2 mv squared. And then up here, where the velocity is 0, the kinetic energy is 0, and the potential energy is at its max, or mgh. This is 1/2 mv squared. So I can say then that 1/2 mv squared, which is the energy at the bottom, is equal to mgh, which is the energy at the top. This is just like the little bead on a string problem, right? I'm just saying that the potential energy here at the bottom is equal to 0, and the kinetic energy at the top is equal to 0. Then I can cancel out my masses. They divide out. I divide every term by m, and I get 1/2 of 10 squared, that's the speed of 10 meters per second, is equal to 10, that's g, times h. Half of 100 is 50 divided by 10, so h is equal to 5 meters. So A is the right answer. That's just like the bead problem, or the roller coaster problem, but just framed in a slightly different way. Likewise, number 2 is just like the one that we did with the frictional force before. You want to try to do it? Yeah, this is fall 19, number 2. I have this cardboard box. It has a speed of 6 meters per second. It has a mass. Oh, I don't give the mass. But there is a frictional force, Fk. Mu k is equal to 0.2. And I want to know how far does it go before it reaches a speed equal to 0. That means that the kinetic energy is equal to 0. So the total energy is 1/2 mv squared minus the work done by the frictional force, which I'm going to call Fk times d. That's equal to 0. Okay, so here, the first term is 1/2 mv squared. That's the kinetic energy. I think you're asking about the second one, right? Yeah, so that just comes from work equals F times D times cosine theta. And what I did is I put in Fk for the force. I have D right there. And I did this negative because I know that theta equals 180. So you're right, I skipped a couple steps there because I knew that my force is Fk. D is still from that equation. And I know that the frictional force does negative work because it opposes the direction of the displacement. Friction force will always be negative. Is that a hand or?
Yeah.
What's up?
If I would have resolved my forces and would have got like F cosine of, I would have kind of did that.
Yeah, in fact, resolving your forces is where the cosine theta term comes from, because it takes the x component of the force. But in this case, there are no forces off axis, so there is no cosine theta term to deal with. But this negative comes about because the angle theta is the angle between the frictional force and the displacement. And the displacement, they're opposite directions, so the displacement is 180 degrees from the frictional force. frictional forces will always be 180 degrees from the displacement. As far as we're concerned, the frictional force will never be in the same direction as the displacement. It will always oppose the direction of motion. So here, I can say that 1/2 mv squared equals FKD. But you're saying, gosh, I don't have the mass, and so that seems problematic. But I can say 1/2 mv squared equals to the frictional force, which is mu times the normal force times the distance. But I'm on a horizontal surface, so my normal force, mu mg times d. So I can cancel out my m's. I divide through all sides by m, and then I solve for d. So that's 1/2 of 6 squared divided by mu, which is 0.2, times g, which is 10. That's 18 divided by 2, which is 9 meters. So A is the right answer. Okay, I know this is all kind of shocking because we haven't really done this in class, but when you see it in class, it'll make more sense. Like right now, it's just sort of like, whoa, what's going on? But just relax, and then we'll see it in class. And then as you practice over the weekend, it'll make even more sense as you go through these.
Where's your time?
No, the 10 right here is G.
So where's your D?
Where's my D? That's what I'm looking for. So I divided both, so I did 1/2 V squared equals mu G D. And so 1/2 V squared over mu G equals D. That's where all these numbers come from. Okay?
So it's just easy to break down the equation to its simplest form, because you can cancel out stuff. 'Cause I
Yeah.
never thought about that.
In fact, you have to in this case because you don't have the mass.
Right.
But you'll find in this chapter that often the masses will cancel out, unless we have a spring associated in the problem. And then that doesn't happen. But we'll deal with strings in class. Okay? Unless you have other specific questions, I think we'll stop there. That's a good preview. I don't want to overwhelm you. Although I probably overwhelmed you a bit, huh? Have I overwhelmed you? All right.
I was a little nervous, but I think I can handle it.
Well, look. So on the old exams, you're looking up to. Let me show you, for example. I'll show you all this in class too. But in exam 3 from fall 2020, you're looking up for the quiz. Actually, yeah, quite a bit for this one. Up through number 18, that's for fall 2020. For fall 19, we're up through number 10. This is fall 19, up through 10. Fall 18. Up through 19, up through 18 rather. Basically, if you see something that says momentum, or if you see something that says collide, or you have a picture of two objects colliding, that means that we're into chapter 6, and that will not be on the quiz. Okay? All right, y'all.